This is lecture 16 where we'll look at solutions of ODEs defined by eigenvalue problems. Uh, I won't go through the definition and also for all those definitions on trivial solutions, non-trivial solutions, as well as non-homogeneous system, I will refer you to the lecture notes. So let's start off by defining what is an eigenvalue problem. So let's say we have this system here. Okay, you have a system of ay is equals to lambda b. Okay, a is basically a coefficient matrix, y is your vector of unknowns, and your b here is your vector of known values. So what is different with this system compared with the system of linear algebraic equations that we have solved in lecture 3 is that it contains a scalar lambda. Okay, so I can also rewrite this equation as a minus your identity matrix multiplied by lambda, and this would equals to 0. I think I got this wrong. This should be y. Okay, so a trivial solution to this kind of system here is the case where all your y values are 0. So if all your y values are 0, then all the y values will satisfy this condition or this equation here. Of course, we are not interested in trivial solutions because trivial solutions is meaningless to us from an engineering point of view. So we are actually looking for non-trivial solutions for this system of equations here. And with non-trivial solutions, what happens is the solution for y is not unique. So when I say the solution is not unique, it means there is more than one solution, or there will be more than one set of values of y that will satisfy this condition here. Okay, so this set of different values of y would depend on what your lambda is. Okay, so for different or for special values of lambda, it will give you different sets of y. So the solutions for y, for if I write it down, the solutions of y for these special values of lambda are known as your eigenvectors. And these special values of lambda are basically known as your eigenvalues. So if you have this homogeneous system of equation and you're trying to solve this for a set of non-trivial solutions for different values of lambda, this is basically known as an eigenvalue problem. So the best example that I can give is the vibration of a string. So the vibration of a string is basically given by this equation here. Okay, so this is a second order ODE where y basically defines the amplitude of your vibration. So let us assume that we have a piece of string here that we have fixed at both ends. So these both ends here are fixed such that this string here will not move from these points, end points here. So if this is x is equals to 0 and this is x is equals to 1, for example, then my y0 would be 0 and my y1 would also be 0. Okay, because we have fixed these 2 points here such that they cannot move. So what is y? Y is basically the vibration amplitude of your string. So if your string is vibrating this way, then this here is your y, which can be a function of x. Okay, so like for example, this can be your y here, and they define the amplitude of your vibration. Okay, so if you look at this system, a trivial solution for this would be y is equals to 0. So what does this mean physically? If y is equals to 0, it means that there's no vibration in your string, and this is not a solution that we're interested in because there's nothing to analyze for a non-vibrating string. So what we want are basically non-trivial solutions. Okay, so I'm going to write here, we want non-trivial solutions, and the existence of these non-trivial solutions would depend on your values of lambda, which at this stage is still unknown. So we'll be considering two methods to solve this type of eigenvalue problems. The first one is the shooting method, and the second one is your relaxation method. You may be able to recall that these two methods have been gone through in detail in the previous lecture, which is on the solutions of boundary value problems. So let's start off with the shooting method. Okay, so we're going to try and solve this with the shooting method first. So let's just write back the equation that we want to solve. We have d squared y. For convenience, I've called this y1, and you see why that is. We have your lambda square y1 is equals to 0. So you have your y1 0 is equals to y1 1, and this is equals to 0. So what we are assuming is we are assuming these two ends will be fixed, and we are assuming the length of the string is 1. Okay, so these are our two conditions that we have here. So this is a second order ODE, so what we need to do first is to convert it into a system of first order ODE. So this can be done by introducing dy1 dx is given by a new variable which we call y2, such that if I differentiate this again, I will get dy2 dx. So if I substitute this back into my governing equation here, what I'll get in the end is this system of first order ODE. Okay, so this is my first order ODE. And we basically would like to solve this subject to the conditions of y1 at 0 is equals to y1 at 1, and this is equals to 0. But unfortunately, we don't know what is y2 at 0, which means we will not be able to solve this first system here. So if you remember from the previous lecture, what we do with the shooting method is we make guesses for what y2 is, and then we solve it to find what is the value of y1 at 1. And we try and see if this value that we calculate here matches the value that is given by your problem. Okay, but we first need to look at what y2 means physically. If you look at this, y2 is basically dy1 dx. What is dy1 dx? dy1 dx is basically the slope or the magnitude of your slope of your vibrating string. So if this is the string that you have initially, and then it is vibrating this way, the slope or the dy1 dx is basically the magnitude of this slope here. So the higher the slope or the larger your dy1 dx, the more steep your magnitude of your slope is. Okay, so that is what it means by y2, and we are actually not interested in y2. Okay, because we are not interested in the magnitude of the slope. Instead, what we are actually interested in is the values of lambda or our eigenvalues, because at this point we are still not sure what are the values of lambda. So instead of guessing what is y2 at the initial point, we'll make our guesses on the eigenvalues or lambda. Okay, so how about our y2 0? Because even if we make a guess on lambda, we will still need to know what is y2 0 in order for us to solve this system of ODE here. So for now, we'll just assume y2 0 is equals to 1, just for convenience. Okay, so we make this assumption, and we make the assumption for a value of lambda. Then we can solve the system of ODE here to find out what is y1 at the endpoint 1. Okay, so from here on, you can basically refer to your lecture notes in terms of how the MATLAB code is set up. It is basically identical to what we have done for the boundary value problems. Instead of initial values for y2, we are basically making guesses for what are the initial values or what are the values of lambda. Okay, so to keep this lecture short, I won't go into the details of the MATLAB code. I would expect you to do that, to go through them by yourself. One thing that I need to point out is this assumption that we have made so far. If you go look at the lecture notes, what we get is we get something like this. Okay, and you have a red line that defines your y1 at 1. So basically what happens is all these points here are your eigenvalues. Okay, and when you assume that y1 at when you assume y2 0 is equals to 1, you can see that this magnitude here is 1. Okay, but if I increase it to 2, you can see that you get a larger oscillation at the initial step. I think I did it wrongly, so let me try and do it again with a different color. Okay, so if you increase it to 2, what you get is you get a higher initial value, which is at 2 now. So it will go something like this. And the thing that you need to note is, although you have assumed different values for your y2, the eigenvalues still do not change. They are still the same positions of your eigenvalues. This means that this this y20 that you assume will not significantly affect your the steps in determining what are your lambdas. Okay, so that's it for the shooting method. I hope you'll go through the lecture notes in terms of the MATLAB codes. If not, you can still go back to your previous lecture, which is lecture 15, where I've done some explanation on the MATLAB codes for the shooting method.